All right, so here we have a sample problem that will deal with control volume versus what I call a control mass approach. The book calls it a system. I'm not sure what it will be called in lecture. But just note that the word system can be a little bit misleading to me. We talk about fluid systems as just being, the general system you're looking at that deals with fluids. And so the use of a system is a little bit confusing to me. So I like to talk about control volumes versus control mass. So for a control mass approach, you're just following a mass of fluid around, and a control volume, you're just sticking with a fixed volume of fluid and thinking about how the fluid flows into and out of that control volume and looking at changes to fluid properties within that control volume, whereas a control mass, you're following the mass of particles and looking how their properties change. Okay, but that'll be gone over in lecture. So this is just a sample problem. It's 462 in your book, which, where is it? There it is. So we read the problem statement. We basically have an elbow with air flowing through an elbow. Uniform speed at the inflow, but due to some separation around the elbow and the turbulent flow involved, we get some reverse flow in a pocket of air in a pocket of the pipe there, whereas we see an acceleration on the far side of the elbow. And so the goal, the question being asked here is to draw the control mass or the system at a later time, and make on the sketch clear what fluid has entered and exited the control volume. So these ideas are, this whole section of the course is definitely a setup for later on. It'll become very vital to have a good understanding and a good feel for how to make these sketches and what's actually going on. But there's not a lot of fundamental fluid mechanics at work here. This is really a tool that we're trying to develop. So here's my drawing, restated the system. Again, uniform flow entering the elbow, non-uniform flow exiting. Let's draw carefully the system and it's specifically the control mass at a later time. Okay, so first we'll note that after this time of 1/100th of a second, we can see where important parts of the flow have moved to. So a particle that was at A at time 0 has now moved a distance, that is the velocity at A times a small delta t. The velocity at A is 10 meters per second. Multiplied by the 100th of a second, we get a 0.1 meter movement of that particle just down in this horizontal direction. Particle at D moves the same distance because it has the same velocity. A particle that was at B at time 0 after 100th of a second actually moves back upward into the elbow because there's this reverse flow in this region. And so, particle B, the velocity at particle at B is 5 meters per second, so it travels less far than particles at A and D. And a particle that was originally at C has now moved even further than particles at A and D because the velocity here is 15 meters per second. To get to the distance involved, we just multiply the velocity times that small delta t. One note here is that if we added another point E, we'll notice that there's no velocity there, and so therefore the particle at E doesn't move. The fluid element at E doesn't move at all. So then our final picture just looks like this. Our control mass at time equals 0 is the black line, kind of the rigid, that would be our control volume. The control mass, or the system of fluid particles, is then moved after 100th of a second to the blue dashed line, where everything along between A and D has moved 0.1 meter forward, and the gap, in here now we've had more fluid entering the control volume. So anything that's here during our if we took a snapshot of the system after 100th of a second, everything in this green shaded region has now been entered, is fluid that had entered the control volume during the delta t, during the 100th of a second. On the exit region, although maybe exit isn't completely appropriate because there's actually reverse flow. So our control mass has a diagonal shape here, a tapered shape so that means that particles that were here have now moved up to this point, and particles that were here have moved out of the control volume. So we get more fluid entering in this reverse flow. So everything in green is fluid that has entered the control volume, whereas the shaded region here in red is fluid that used to be in the control volume but exited it, the control volume during the 100th of a second. Okay, so one thing to note: we're dealing with air flowing through an elbow. The volume of fluid entering the control volume, everything in green here, if you added up this control volume, which is actually quite easy, this is just a rectangle and a triangle, and you compared that to the volume of air that's exiting in red here, they're not equal. In fact, there's more entering than exiting. So that means, just use your common sense. If we have more air, volume of air entering than exiting, the air must be compressing inside, right? And that's possible because we're dealing with air. So around the bend, there must be some compression in the air to maintain well, we'll see here going forward, to maintain mass conservation. Okay.